This will be a video to help you assemble the ray tracing diagrams and remember focal lengths and things like that. So we'll start off with convex lenses. And remember, the focal length for these are positive. Okay, and let's take a look at our ray tracing diagrams and see if we can come up with keywords here. The idea is that we would remember what to do. So we have a convex lens. We're outside the focal length. What do we've got? So we have a parallel through focal, and then a ray through the center. So maybe our keywords could be parallel, and then our next keyword could be focal point, or just say focal. And then maybe straight through. So do something like that when we, write it in your notebooks like that. So just kind of like label this as convex, outside the focal length, do parallel, focal, and then straight through. Now, to save time, I'm not going to actually write our keywords. I'll just say them obvious enough so that you can write them down. So now we're inside focal point. So it looks like we're up, parallel, and then parallel, focal. So write that down as up, parallel, parallel, focal. And then you just trace your rays backwards to find out where the image is going to be. So we're going to trace this back to there, retrace this one back to there, and there you have it. There's your image. The image is always formed where the light rays intersect. So hopefully these keywords are going to help. So again, up, parallel, parallel, focal, and then from before we're going parallel, focal, and then straight through. Let's see what else we can do here. So if we go to the concave, remember that focal length for these guys is negative. So make sure you're recording that. So let's see if we can get a pattern to this. All right, so and here it doesn't matter where we're at. We're never going to get a real image out of these guys. So we're going to go parallel, up, and then I guess angle downwards, then flat. So let's see if we can come up with a way of recognizing this. So parallel, up, and then maybe to the middle, flat. So those might be keywords there for you to write down for the concave lens. Okay, and let's summarize our equations for lenses, which will also be the same for mirrors. So our equation is 1 over the focal length equals 1 over the object distance plus 1 over the image distance. And magnification is equal to the minus image distance and divided by object distance. Now remember, when image distance equals positive, you have a real image. When the image distance is equal to negative, you've got a virtual image. Now this will be true for mirrors and lenses, these equations. Okay, and also remember that magnification, we'll take the absolute value of magnification, is equal to the height of the image divided by the height of the object. So if I have a magnification of 2, that means my image is going to be 2 times higher as my actual object. Okay, well, let's move on to mirrors. And again, all these equations are the same, okay, but we'll start with the focal point. The focal point of concave mirrors is positive. So we're outside the focal point right now. So let's see, the first ray is parallel, and then through focal. The other one's focal, parallel. So those might be good keywords to write down. So parallel, focal, focal, parallel. And again, where the light rays intersect, there's where your image. Notice how it's upside down. So that's when we're outside the focal point. Okay, what about inside the focal point? So here we are inside the focal point. Remember, we'll get a virtual image anytime we're inside focal point, and that's true for lenses and mirrors. Okay, so let's see, what do we got? So we got up and then parallel. Okay, and then we have one that is with the center of curvature. So up like that, and it comes right back. See that? And then we see that our eye will trace back to where those light rays look like they're coming from, and then get image right there. Notice how it's upright. Okay, so what keywords can we have there? So up and parallel, and then center of curvature. That might be a good reminder. So up, parallel, and then center of curvature could be other keyword. And remember to trace the rays back. So write some good keywords to remember how to draw these light ray diagrams. Let's go to a convex mirror. Convex mirror is just the other side of a concave mirror. Okay, that's all it is. Okay, so we'll always get a virtual image for this because focal length is equal to negative. It's always a negative for these. So we're on the other side. A good convex mirror could be a Christmas ornament, those bulbs you put on a tree. When you look inside those, you can always see a virtual image. All right, so what do we have here? So we have one going straight down this way and back again. It looks like that's at the center of curvature. Then we have a flat or parallel, and then it bounces back upwards. And then we trace that to the focal point. And where those two light rays intersect, we have our image. Now remember, this is a virtual image. Okay, so how can we remember that? So I guess one is center of curvature. It's aimed right at center of curvature, so maybe center of curvature. And the other one is parallel and reflected up and focal point. So maybe we want to say parallel, up, focal point for the keywords for that. And again, I'll let you decide what to exactly write for that. So hopefully, these ideas help you remember, and write all these in your formula bank. That'll help you remember how to do these things. And one last thing for spherical mirrors. I just want to remind you there's one more formula for those. The focal length is always equal to the center of curvature divided by 2. And the center of curvature, just think of it's the radius of the circle that would be made if the mirror was completely spherical. All right, that's how you handle ray tracing diagrams.